Yeah. Could you make sure it's like recording? Like if it turns off. Okay.
Okay. Hi guys. I don't know. Have you guys signed in yet?
No.
Okay. So we have like a tiny URL. I don't know. Sign in now. Let me know. Is there anyone who needs this up? Like the tiny URL link. Anyone who still needs this up? You're good. Okay. All right. I guess we can get started. So, hi guys. This is our second lecture. It's going to be an introduction to machine learning. Out of curiosity, how many of you guys have like done any machine learning conceptually? Tried it? Like anything like that? Okay. That's fine. So we'll be covering it like ground up. So hopefully not too much of it is repetitive for you. But yeah. Okay. A couple of like logistic things to get out of the way. I think most of you guys present have really done your, most of you guys have done your deposits and safety trainings. Not sure what that says about like biased samples or anything like that. Maybe people who come to lecture do the deposits and safety trainings. But we still haven't received some, so if that's you guys, please submit the forms as soon as possible. I've linked them here. They're also like where we sent them originally. I think the deposit form is in the announcements channel, and the safety trainings, there's always more details about it in our syllabus, so refer to those. Since we managed to get everyone added to their team group chats by now, we're gonna like chase you guys down if you haven't done them in those starting tonight. So please try to get those done as soon as possible. Lab 1, most of these faces I recognize from the work session. You guys did a really good job. I honestly thought it would be like a little more disastrous, but you guys did a good job getting the sports off and stuff like that. For those of you guys that had trouble SSHing, I believe we figured out the issue now. So I guess this is a little out of date, but we finished, or we figured out the issue, and then we'll actually be like updating your pies tonight. With like the necessary configuration, so you can probably come in anytime and then finish your SSH, take a screenshot, send it in the checkoffs, and you'll be good. Here's a note about work sessions as well. So as a general rule of thumb, we have one work session per lab, unless if we notice like people not making so much progress in the first work session, and then we might do another one. We will like get a schedule for you guys up. It'll be tentative, but we'll like post like a list of days that like, you know, these are probably going to be Pocket Racers days for you guys, and we'll get that out tonight in the announcements channel. So yeah. Okay, on to content. So you guys probably heard the term artificial intelligence thrown around a lot. So artificial intelligence is basically like, you know, computers doing human tasks. The way this relates to machine learning is like, you guys probably have heard of neural networks at one point. Neural networks were like meant to like emulate, you know, the style of our brain and how it works and stuff like that. So this is like the primary motivation behind studying machine learning, is getting like machines to do more complicated tasks. So there are a lot of types of machine learning. The divisions between them are somewhat actually a bit arbitrary. So we have three main types: unsupervised learning, supervised learning, and reinforcement learning. Supervised learning is what we're going to be focusing on mainly for Pocket Racers, actually pretty much exclusively. The reason why we call it supervised is because for every like data point that you have, it's going to have a label on it. So like, let's say I record some data points on like, I don't know, like birth weight and like birth, is it length? Size? I don't know. And then we would want to label those data points with a label, like I don't know, like this baby is, what do people label babies with?
Another analogy is you have like playing cards. I don't know why you went for babies.
I don't know.
If you have like playing cards, you're like, oh, this is King of Hearts. Oh, this is like Queen of Spades, or like this is a 7, etc., etc.
Yeah.
Like what the label would be.
So the data exists with a label. Like similarly, unsupervised learning, there's no label. So you'd want to look at data, and then you want to build patterns from just looking at the data. So your machine learning algorithm is driven by finding patterns in the data. It's actually a very subtle distinction, because unsupervised learning, most people just like use supervised learning techniques to deal with unsupervised learning. So these divisions are pretty arbitrary. The last one is reinforcement learning, which is like you can think of it like analogous to natural selection. It's like basically something will do something. If it fails, it's not good. If it doesn't fail, it's good, you know? And then through massive amounts of trial and error, you can build a model that'll perform some sort of task. Just to further reinforce that the divisions are somewhat arbitrary, I believe there's a form even called like self-supervised reinforcement learning, just to show that, like, you know, supervised learning is really the main focus of the industry today. There's a machine learning pipeline. We will be performing this over the course of the year multiple times. We're going to acquire data at one point, and then we're going to want to clean it so that we can put it into our machine learning model. That usually involves things like getting rid of extraneous data and stuff like that. Then like we format it so it's acceptable. These are pretty much the same step. And then there's this process of training and validation, which we'll get into this lecture. And then eventually, training and validation, you go through multiple times, you build your model, and then you test it on something. And then once you test it on something, find out that it does good with the test data, which we'll explain later, you get to use your model. So this is probably going to be a familiar example, and the most frequent way that machine learning gets taught is with linear regression. So I'm sure, I mean, you guys have heard of linear regression? Yes? No? Yes? Okay, so usually we have a different name for this. It's like line of best fit, right? So in machine learning, we're going to consider like a sort of different context of looking at this. We're going to be like, well, how do you find a line of best fit, right? Like, what does best fit truly mean? So we have something in machine learning called a loss function. And what a loss function does is it'll basically quantify how well, or actually it's called a loss function, so it's actually going to quantify how not well something is doing at its current task. So you guys may have seen, okay, so this is just to reinforce the fact that, like, the lower the loss, the better you're doing. So loss function is something you want to minimize, which should hopefully be like a red flag for you guys. What we can do is we can use something called mean squared error. I'm sure you guys have probably seen this as well. So basically what this formula is representing here is for every data point that you have, you subtract it by what your current prediction is. That's what y hat is. And then that quantifies like the difference, I guess like distance on the y-axis as well. We have an illustration of this later. But you square it as to not have the negative terms and positive terms cancel out. And then you take the mean of it. It's called mean squared error. So here's, all of these slides will be posted with the intent of, like, you know, you guys can look at this for posterity and get some idea of what all the formulas mean and stuff like that. So yeah, this is what I was talking about. This is like the distance on the y-axis. This is hopefully a very intuitive way for you guys to quantify how well your line is doing. Like if one of these distances is really big, your line's probably not doing a good job. So you want to minimize this as much as possible when you're choosing your line of best fit. So let's take a look at how we might go around doing that. So in machine learning, we have a process called gradient descent, which is essentially, how many of you guys know what a gradient is? Anyone brave enough to take a stab at a definition? Come again? Yes, derivative of the curve. That's a perfect explanation. So this is precisely what we're going to do. We're going to take the loss function, and then we're going to take the gradient of it, which is just a fancy way of saying take a partial derivative of the loss function with respect to the different terms in it. So the slide, yes. Okay, so equation of a line is up here. We're going to use A for the slope and B for the y-intercept. And then basically we want to minimize our loss with respect to these terms, because that's what we're defining as a line, because those two like parameters define the line. So we take the gradient of the loss with respect to those values in order to minimize it. Everyone following this logic so far? Any questions? Okay, let's keep going. Oh, yes.
This might be out of scope, but is there a reason we need to, is there a reason we'd rather square it as opposed to just taking the absolute value?
So it exists as a different way of quantifying error. So most loss functions are like many of them. them. They all have their pros and cons. I don't actually remember the advantage of like absolute value error versus square error. In this case, I think mean squared error is generally more popular, more used, so just sticking with that. But yes, it is a valid way of determining loss. There are many valid ways of determining loss and how well your functions do, and stuff like that. Good question. Anyone else? So, let's say we take our loss function here and just plot it out. So this is a parabola because, you know, it was a mean squared error function. So, yes. So when we take the, okay, let's first look at only the slope, which we had as a. When we take the derivative of loss with respect to a, if we see that the value is greater than 0, which is represented by like this line having a positive slope, we can see that like if we were to decrease a, which is to say that we were to shift that point left on this parabola, it would cause the loss to decrease. And hopefully it's evident that like that rule is foolproof. Like if at any point the point is on the right side of this parabola, it's going to have a positive slope. Therefore, if you decrease it, you should be decreasing your loss. This logic is pretty much fundamental behind the idea of gradient descent. Similarly, the same case exists on the left side of the parabola. When the slope is negative, if you were to increase a, you would cause the loss to decrease. Any questions here? This is like the main theme of gradient descent. Okay. So, if we take this logic, which we somewhat established as foolproof, and we just repeat this step over and over again, we should converge to a minimum value in theory. And this is the process of gradient descent. So, what we have here is we have like a slope value, right? And then we take the partial derivative of the loss with respect to that slope value. The value we get should be positive or negative depending on whether it's on the right side or the left side of the array. We have this minus here to indicate like, to get the direction correct. So for example, right, if this partial derivative is positive, that means that like, it should be on this side. So we want to decrease the slope to arrive at a value that provides a lower loss. So this negative sign exists to like sort of say like, okay, if the slope is positive, we'd want to subtract from our current value of our current slope value, which is a. And then that would provide like our next slope value, the next thing we want to try. And we just keep repeating this process until we arrive at a minimum. So you may have noticed the other variable that's being introduced here, which is alpha. Alpha is something we call the learning rate. It's actually called a hyperparameter. So earlier I said parameter was a way of describing A as slope and B as y-intercept. Those are like the parameters of our model. So in this case, our model is a line. So its parameters are the slope and the y-intercept. A hyperparameter is different because it's a value that we choose. Like you will choose the learning rate of your function, of your gradient descent like process. Hyperparameter is basically just a fancy way of saying this is something that you choose when you're training your model. Any questions on that? Okay. So, this is the intuition behind why you might pick a certain learning rate over others. So, if you picked a really large learning rate, you might have it so that every time you make a step in gradient descent, you're going to overshoot where the like minima of your local the minima of your loss function, and then you might overshoot it and you might diverge from the minimum if your alpha is too large. But conversely, if it's too small, you may never reach it, or it just might take too long to reach it. So it's like an optimization problem, which is why hyperparameters, there's lots of stuff on hyperparameters and choosing them and stuff like that. You'll get the chance to experiment with this in our second lab and stuff like that, so this is the kind of stuff you'll be doing. Any questions here? Yes?
Kind of curve, but which kind of shape of curve do you want to achieve optimally?
The shape of the curve we want to achieve optimally for the loss function, or?
Yeah. Because like we're decreasing or increasing the slope.
Okay, I see. So the question is like optimally, like what are the values that you want to decrease the current slope by to like reach the minimum as fast as possible? That's a question where you would like sort of experimentally determine at what point do you reach the minimum value fast enough. There isn't so much like a set process for reaching it as quickly as possible. It's chosen in this case for mean squared error and linear regression. You'll be choosing your alpha, and it will just be determining like how much your slope moves on this loss function curve. It'll be determining how much the point on this loss function curve moves per iteration of gradient descent. So like, there could be a perfect hyperparameter to choose, but it's not particularly easy to detect before you've done it. Did that make any sense? It's a job.
Would you have to keep alpha fixed, or like as you're going, could you change the value of alpha depending on like how close you're getting to your mean points?
So the question is like whether alpha can like change over the course of training your model, which is the process of gradient descent. It's an excellent question. This is something that we'll cover later, but alpha can change. It's through processes that we basically have different names for different types of gradient descent. One of them that you'll probably explore over the course of this year is called momentum-based gradient descent. It's basically this idea that's like, okay, let's say that you made a step like this way, and it's like, okay, I've noticed that like I'm still on the left side and A still needs to increase for me. Okay. You could have an algorithm that would basically say like, okay, I'm still on the left side of the minimum, and I would want to change my alpha so that it would decrease faster the next time. This is the idea of like momentum-based gradient descent. You can sort of visualize it as like a ball rolling down. It's gonna pick up speed as long as it's still on the same side of this. So this is like an algorithm that we choose. So yes, this is something that is done, and it's like, in practice, a pretty good idea. Any other questions? Okay, so here's a summary of all of our equations. You don't really need to like, these slides will be posted. This is basically for posterity of like when you're doing the lab. It'll be really easy to refer back to this. Okay.
It's not a bug, it's a feature. We're gonna be learning about features. So features, so before we were talking about like X and Y, and those are for if we have just like a single input, but let's say we have multiple inputs we want to take into account. So let's say we're measuring like the growth of a plant, and before we were just seeing like how much it was watered, but let's say we have other factors we want to consider, like how much time it spent in the sun or the kind of soil it uses. So that's an example of like when we'll use this, and like how we can use multiple features for linear regression. So in order to do this, we'll be using matrices and vectors. Have you guys taken like 32B? Is that it? Or like you guys are familiar with matrices and such? Okay, that's good. So basically what we're doing is, so theta will be of length of the number of features, so like the number of like traits we're trying to observe, so like the sunlight, the soil, and the water. So the number of features would be 3, and then we add 3 plus 1, so we have a 4 by 1 vector representing the weights of our model. And then let's say n is the number of data points, like how many plants we're looking at. So the x would be a matrix representing our input data, and that would be n by f plus 1, so our data points by the number of features plus 1. Y is just our actual outputs, and y hat would be our predicted outputs of the model. So and in order to find y hat, we have y hat is equal to x times theta. Yeah.
Why is it f plus 1?
So remember like y equals mx plus b, how there's like a constant there? Like from the way that we're multiplying, in order for there to like be a constant, you have to have the 1 as like a bias term. Does that make sense? Yeah. It also makes sense when we're doing the like matrix multiplication. So So we have this example here. It is a book rating based on the pages in the book, the year it was published, the dragon count, and whether or not it's fiction. Does anyone want to guess what X would look like in this scenario?
Referring to the matrix.
Yeah. What are our inputs for this? Sun. Oh, Harry.
So it's like rows and columns of the rows are the 0 to 5 items.
Yeah.
The columns are features.
Yeah. Exactly. So it would be these 6 data points, and then it would be 1, 2, 3, 4 features. So what about Y? This one is pretty easy. Yeah, Holden.
Oh, it's the rating, right?
Yeah, that's the rating. So that's what X and Y would be. Ta-da! Okay, so now we're going to be looking at theta and y hat. So let's say we had the value for our model. This is like the predicted y value. And each of these letters A, B, C, D, that's like our inputs from the data. So those are going to be changing. And then these numbers that you're multiplying each letter by are the weights. Is that part clear? Okay. And that's how we get our predicted y value. And so what would be theta in this scenario? What are our weights? Harry?
Like the coefficient
Mhm.
from the ABs.
Yeah, so it's going to be a vector with these numbers for the coefficients for them. And then what is y hat? Laura?
At the particular values.
Yeah, exactly. Ta-da. Oh yeah, this is like, so remember A, B, C, D, referring to your question? This was the coefficient for A, this was the coefficient for B, this was the coefficient for C, and this was the coefficient for D. But we need this bias term in order to get that constant. Yeah, that one like didn't have a data point multiplied by. It's also kind of like convention, because remember how it's like y hat equals x theta, x times theta? That just makes it easier because you're multiplying it like that as opposed to having to like add in like this extra constant. And so this is how we can rewrite our equations. Yeah, I feel like if you know like how different things connect to each other, like y is like the actual value for y, and then ax minus b or ax plus b would be x theta, and yeah, these are just all the equations converted, I guess, into matrix form. Okay, so we talked about using gradient descent to find the answer, but another thing you can do is actually, so we have our loss function, and so what we can do actually is like set our loss to 0, and then we can solve for the best theta. So that's what we're doing here, because when it's 0, that'll be like the minima of the parabola. Yeah, this is called the normal equation, and this is like a good way. It's not a great way to do it, but you can do it this way. The problem is that it's very computationally intensive. So like we're doing a lot of like matrix multiplication, as you can see here, and like if you have a really big data set, that would take a lot of effort and a lot of time. So that's why using gradient descent is often still used, despite having this way to solve for them. Any questions?
Is it me?
I don't know. Click it. It might be.
Okay. So, Up next is logistic regression. I really can't tell you why it's named this because it's not actually regression, but we'll be diving into it anyway. Okay, so one might ask, okay, we've talked about regression so far on like a continuous line, and it's like, what if you wanted to do a classification problem, which is like you have a certain number of categories, how would you go about predicting them? So we have logistic regression for this, which again, I've explained is a bit of a misnomer because you're not actually doing regression, you'll end up predicting a category. So we have like this example with eggs here. Does anyone want to give an example of like how we might want to like encode these values into like, or encode these categories into like discrete variables? Like how would you go about representing all these different categories numerically? Any takers? No? Okay, that's fine. The most obvious thing that might be coming to your mind immediately is like, okay, what if we just called, what is that, soft-boiled eggs, like 1, and then the next category 2, next category 3, next category 4. This is seems like a pretty intuitive way of doing things, but we'll see that that's actually probably not optimal for what we're trying to achieve. So, yes, this is what I was talking about. So, there is something called one-hot encoding. How many of you guys have heard of this before? Okay, fair number. Basically what it is before when we were talking about features, this time your feature will be like a category, and it'll have a 1 in that category if it's true, and a 0 in that category if it's false. The reason why we call it one-hot is for that entire series of like columns. So here, like on this output side, you can't have an egg that's hard-boiled and fried. So this is the reason why we call it one-hot, because there's only going to be one in that in that classification of like categories and stuff like that. So there's a reason actually why we choose this over what I was talking about earlier, which is just doing the 1, 2, 3, 4, 5 to encode the different categories. So why don't we do this? Does anyone have any guesses actually? Because this is a pretty tricky question. Yes.
You don't want to create any indication that scrambled is for some reason greater than fried, or that there's some sort of numerical relationship between the categories.
Perfect, exactly. So like in this case, hard-boiled and scrambled are further away from each other. But if your model predicts it wrong, it just got it wrong. It shouldn't recognize that there's a difference of 2 between these. It should still be recognizing that, like, you know, there's not particularly any difference between if the model predicts hard-boiled and the egg is in fact fried or the egg is in fact scrambled. We don't want that sort of like numerical relationship that the integers have, which is why we go with one-hot encoding. Did that make sense? Okay, so this is just putting it into words. When we start going about calculating our errors, we don't want our model to think that it's more wrong for making a prediction of like a category that's further away numerically. So, basically, we've learned linear regression so far, so it might be intuitive to try to use linear regression like as an approach to solve this problem. So like, let's say you wanted to classify something as not yummy and yummy. Imagine you had a line, as we did in linear regression. How might you use that line to predict between 2 categories, let's say? Like, what would be a fairly trivial way of saying, like, oh, okay, like, this is yummy or this is not yummy when you have a line of continuous values? Any takers? Okay. What a fairly like naive answer to this might be is like, okay, let's say we take values above, I don't know, like 5, and we call those eggs yummy, and then the values below that we call that not yummy, right? That would be a valid way of taking our continuous line and converting it into something that's binary. However, there are a lot of problems with this, right? Like, as soon as you make that like sort of like if statement of like if it's above 5 or if it's below 5, it's yummy or not yummy, it doesn't tell us any information about how likely that the model is certain that its prediction is correct or not. So like, if your linear regression model said like 7,000 or something like that, it'd still get classified as yummy. So we're still actually losing information here when we try to attempt something like this. Mean squared error also wouldn't really work here because, like, again, for reasons that I just said, like the values or the information in the values still kind of gets lost. So the last point here is actually something about, like, let's say we use the sign function. So instead we said if it was positive or negative. It's actually not differentiable. So earlier when we took the derivative of it to like see like the loss and the curve that it created and how we converge to a minimum, we wouldn't be able to do it that way anymore. So these are all problems. So we have a function for this. It's called the sigmoid function. How many people have seen this before? Okay, nice. The sigmoid function is a pretty robust way of determining between binary categories. So here's the equation in vectorized form. So this x is still a matrix and this theta is still a matrix. And basically what it is we have 0.5 as a value indicating complete uncertainty and 0 and 1 indicating, or sorry, yeah, wait, I said complete uncertainty, right? Okay. 1 would be complete certainty for yummy and 0 would be complete certainty for not yummy. And everything in between would be, you know, just less certain versions of those. So this is pretty much what we're looking for here. This function is accompanied by, oh, okay, so here are just some values of like how that equation would work numerically. So yes, basically what you're doing is this x matrix multiply theta here, this is giving you like that linear regression line earlier. Like this represents a line. Once you pass it into the sigmoid function, like you see here that it's the argument for the sigmoid function, you'll convert it into this line. So let's say you did regression, oh, sorry, wrong way. Let's say your regression output was -10. You'd be pretty confident that your egg was not young. And here's just a table of what that looks like numerically. So we have an associated loss function with the sigmoid function. It's called the cross-entropy loss function. The details behind this we're not going to fully talk about to you guys. This is probably just going to look like a magic equation to you guys. But it does quantify the loss between your predicted value and your true y value. You'll be using this instead of the mean squared error when you're doing binary classification tasks. Any questions? Okay, so we haven't given you the full solution here because it might be entertaining for you guys to try it out. But we've taken some partial derivatives with respect to certain values, like the loss with respect to the predicted value, and then with respect to, is that correct? Okay, this will be here and correct when we give you guys the lesson. But yes, essentially you want to get the partial derivative of loss with respect to the entire vector of weights, because this is, again, what you're trying to minimize. So it's just different, but it's the same concept as the mean squared error. Does that make sense to you guys? Okay, and lastly, we should mention non-binary cases. So if you have multiple cases, we have something called the softmax, or sorry, non-binary like classification problems. So if you have multiple classes that you're trying to predict, like let's say you're trying to predict whether something was out of like 5 classes, we have a softmax function. So softmax is detailed here, and then there's an associated loss as well. Again, these equations may just seem like they're coming out of nowhere. Some of you guys may be familiar with the softmax function, but this is essentially like a way that's very similar with the sigmoid function, where you have certainty as like your sort of metric of the numerical values and stuff like that. Any questions here? Okay, well, guess I should put it here.
Okay. So now that Justin's taught us how to train on our data, yeah, so this sounds like pretty easy. We just do gradient descent on all of our data points, and then we're ready to throw our model into the world, right? No, actually, oh, could you go to the next?
Oh, sorry.
So if we did gradient descent on our entire batch of data, it would be really slow and it would take a lot of time. So instead we do gradient descent on smaller batches of data. Those are called mini batches. And we evaluate and update the weights that way.
Oh, sorry. I did it
An
behind you.
extreme example of mini batch gradient descent would be choosing a batch size, so the number of like points you're doing gradient descent on, to be 1, and that would be called stochastic gradient descent. So basically, you'd be applying gradient descent on like a random point, and then like updating the weights, and then doing it again, and trying to get closer to your to the right answer. So this is kind of like an example of like how these different gradient descents work. So for batch gradient descent, which is like the one with like all of your data points, it would work. All these would work. It's just that this one would be really slow, but it would get you there. This one, well, let's go with this one. This one, since you're only doing one data point at a time, it's gonna be really erratic. So it's gonna be like jumping around, and it's gonna have a lot of noise because of this. And that's why we kind of lean towards mini batch, because it's kind of it's not as erratic, but it's also gonna be a little bit faster. Yes. And then, so another thing is also gonna be like another hyperparameter that we're going to be messing with is the batch size. So how small or big you want the number of data points in your gradient descent to be. Okay, good. So now, now that whoa, spoilers.
Sorry.
Okay, so now, we've done that. We have a training error that's really small, and like, we're good to go. That's not actually true. I'm gonna liven this up with a scenario. It's a true story. So I'm super good at Mario Kart. I practice Rainbow Road every single day for 6 hours. I can do Rainbow Road with my eyes closed. I'm so good at Mario Kart. And then Justin challenges me to like a tournament. And then we go on like three roads. We go on Rainbow Road, I don't know, Moon Falls, I don't know, Luigi's Mansion. and then we race. Do you think I'll win? Yeah? What if I've only practiced on Rainbow Road? No, I don't think so. So this was like a convoluted example of like overfitting. So because I didn't practice on any of the other roads, when you get me to a new road, I'm gonna be like completely out of sorts, like because I'm totally accustomed to one kind of scenario. So basically this can happen with your data as well. This is called overfitting. So this is kind of like an example of looks. So like this is like, it's like in the middle, right, in between all the data points. But then it's getting a little bit too specific to this data. And so this like this is more complicated and also wouldn't apply to new data as well. It's not as like applicable. And some things that could cause your data to be overfit is if the data set is really small. So if you only have like 2 points, it's gonna be a line between those 2 points. It's not really gonna give a good indication for like any other data. Too much training. So yeah, if you do too much training, yeah, it's just gonna be like looking over the same things and finding very specific patterns to the data that you have. And then also, if you have an overly rich feature space or overly complex model. I think that's... So what are some ways that we can prevent overfitting? So what we can do is we can train our model, and then we can take our data set and then set some data aside for testing later. So we'll train our model, and then once our model is trained, we can see if it works on new data by using the test data that we had set aside earlier. Yeah, so that's how we can see if our data is overfitting or not. So if we find that like, let's say our training error is really low, but our test error is really high, that indicates that our model is overfitted because the test data is, the training data is really low and the test error is really high. And if we find that the training data is really low and the test error is really low, that's a good indication that we have a good model. And then if we have a high training error and a high test error, then we need to go back to the drawing board because not great. So, oh wait, any questions about that? Okay. So let's say we train our data. So we have data for training and we have data for testing, but we want to make sure that we're able to check our trained model besides the test, because we don't want our model to be like also too tailored to the test data set. So what we can do is we have, in addition to the training data set, we put some data aside to be the validation for data set. And then we can use this for our training model as well. So this is the pipeline we saw earlier. So you have the data, you clean it, all that good stuff. And then you train your model, and then you validate, and then you continue to train it, and then you can test it again. This, because the testing would be like totally super fresh data. Oh, do you have a question?
Yeah, I was just thinking in the context of our project, like, are we gonna be trying to generalize to any road, or are we gonna be fitting to like a very specific road?
So for right now, I think we have a track, so it'd be a specific road. But I think something that could changing it is like, we also have signs indicating like which direction and such. So as of right now, but the subject to change is like maybe putting the signs in like different areas, and so it's not specific to a certain path. Does that make sense?
I think so, yeah.
So a good way to do this is or a good way to validate multiple times is to divide our data into chunks. So we have all our data up there, and then we put aside some test data for later, and then we divide up the rest of our training data into different folds. This is called K-fold cross-validation. So what we're gonna do is we have fold 1, fold 2, fold 3, fold 4, and fold 5. And what we're gonna do, we're gonna train on fold 2, 3, 4, and 5, and then we'll validate with fold 1. And then we're gonna do something similar. We're gonna omit fold 2, train on all the rest of the data, and then validate with fold 2. And then we're gonna do that with all of the folds, just to kind of see how good our model is. Yes. Ooh. Oh yeah, and then once we're done, we can, once we have our model done, we can use our test data. Is there any questions about that? Yeah, Ryan.
When you're doing the folds, do you restart your retrain it from the ground up for each split, or do you keep the previous training information and just move on to the next fold?
Like the same.
Like, do you use the same parameters you trained up on the first split for the second split, or do you start with like random parameters in each split?
I think so something that's nice about validation is that it gives you a chance. Actually, I think it is, you're not starting from scratch.
Okay, cool.
Yeah.
It depends on the context,
Yeah.
actually. Like, this is probably a bit beyond the scope of the lecture, so if you're more curious, I'll
Gotcha.
All right. Okay.
Oh, are there questions?
Okay. That's it for us. Well, I guess there's no questions, but if it's not about the lecture, it's fine too. Lab 2 should be coming out soon. It's going to have a due date pretty far into the future. I know you guys have midterms coming up and stuff like that. I wouldn't particularly procrastinate on it. If you're not super experienced with Python and you're gonna struggle on a lab, it'd probably be this one. So whenever you have time during this chaotic midterms week, I'd recommend just trying to knock it out before leaving into the last second, because you wouldn't want the time to particularly conflict. Anyone have any questions about, like, I don't know, like lab 1, groups, stuff like that?
When is lab 1 due again?
I believe it's next Wednesday, a week from now, November 1st, 11:59 p.m. Yes.
sorry, I wasn't at the work session. Do we like all have to do it individually?
Oh,
This lab is individual.
do you, lab 2 is.
Yeah. Oh, sorry. Did you mean lab 1 or? So lab 1 where
Mostly,
you're
yeah.
building your car is the team that you do as a team.
Okay.
But the lab based on this lecture is gonna be individual.
Okay. So we're okay.
So for those of you guys who are watching, and everyone who's here, if you couldn't make it to the work session, the most important thing is you communicate with your team to figure out like where your team has gotten. Like obviously you guys only have one car, so you are making team progress on it, but we strongly encourage you guys not to like do like something where like one person does one lab, one person does the next lab or something like that. Lab 1 should very much be a team effort. Even if it couldn't be because you couldn't make the work session, you should still see how far your team members have gotten. Any other questions?
Solomon?
So our lecture is gonna be like every Wednesday, or on Wednesdays or Mondays?
I think so. Originally I had them planned for Mondays, but I think we should do Wednesdays, right?
Our next one is currently scheduled for Monday.
Yeah.
We will send out like a tentative like list of our upcoming events for this fall. But it's subject to change and we'll notify you when they change.
Could we? Do you guys have a preference for Mondays or Wednesdays?
I feel like Monday.
Really, you prefer Mondays?
Okay.
Would that still be the answer if it was like work session Sunday and then Monday lecture?
Yeah.
Okay.
Okay. Well, that's a relief. Okay.
So next lecture will be on Monday then. Not soon.